This tutorial is all about pipelined ADC design. Before we dive in, let's quickly unpack that title. First, what is an ADC? It stands for analog to digital converter. You can think of it as a translator. The world around us is analog. Things like the sound of your voice, the temperature in a room, or a radio wave are continuous signals. But our computers, smartphones, and almost all modern electronics operate in the digital world, which is all about discrete values, basically ones and zeros. An ADC is the crucial bridge between these two worlds. It takes a continuous analog signal and converts it into a digital representation that a processor can understand and work with. So, what does the pipelined part mean? This refers to a specific type of ADC architecture, a particular way of building it. Imagine an assembly line in a car factory. Instead of one person building an entire car from scratch, the work is broken down into a series of stages. One station puts on the wheels, the next installs the engine, and so on. A pipelined ADC works on the same principle. It breaks down the complex task of analog to digital conversion into a sequence of smaller, simpler steps. Each step is handled by a separate stage in the pipeline. As the signal moves through, each stage refines the conversion a little bit more. This assembly line approach is extremely efficient and allows for very high conversion speeds, which is why pipelined. ADCs are essential for applications like wireless communications, medical imaging, and high-speed data acquisition. Throughout this tutorial, we'll be exploring exactly how to design these high-performance converters, looking at the challenges and the clever solutions engineers have developed. This page provides a clear roadmap for our entire discussion on pipelined ADC design. It outlines the logical flow of the topics we're going to cover. We'll begin with a review of pipelined ADCs. This is our starting point, making sure everyone has a solid understanding of the fundamental architecture and operation of these types of analog to digital converters before we dive into more advanced topics. Next, we will explore the impact of scaling on data converter design. This is a crucial section that addresses the core challenges in modern electronics. As we make transistors smaller and smaller to fit more on a chip, a process known as scaling, it introduces new problems for analog circuits like ADCs. We'll examine exactly what those problems are. This leads us directly to the next key question: why calibration? After understanding the negative impacts of scaling, this section will explain why we can't just rely on traditional design methods anymore. It will build the case for needing a solution, and that solution is calibration. Once we've established the need for it, we'll move into the specifics. We'll start with the basics of digital calibration techniques. Here, we'll learn the fundamental principles and concepts behind using digital logic to correct for the errors in the analog parts of the ADC. Following that, we'll broaden our scope with a survey of digital calibration techniques. This section will look at various methods and approaches that have been developed. It's less about the basic theory and more about the practical application and variety of techniques you might encounter in real-world designs. Finally, we'll bring everything together in the conclusion, where we'll summarize the key takeaways from this entire tutorial. So, you can see a clear story here. We start with the basics: identify a problem, justify the solution, and then explore that solution in detail.